This meeting is being recorded.
In this next video from chapter 16 on acid-base equilibria, we'll take a look now at weak bases. So in the beginning of the chapter, we had a quick overview of acids and bases in general. We started with strong acids and bases, then we moved on to weak acids. Now we'll take a look at some of the similarities, some of the differences now with weak bases. So instead of reacting with water to produce hydronium, now we're going to see that bases will produce hydroxide ions. So let's take a look here at some common weak bases we may encounter, and instead of Ka values, they will have Kb values. So the same way that Ka tells us a weak acid dissociation constant, or the percent that will ionize at the end, we can utilize Kb to tell us how much our weak base, such as ammonia here, would ionize in solution. So let's look at what a dissociation of our weak base will look like. So we have our base, our ammonia. We add this to liquid water. We get this equilibrium to establish. We're going to get our conjugate acid. So luckily we're given that here, so we can just quickly know we're going to gain a proton, and we have ammonium, NH4. So this is my conjugate acid, and then we know we're going to get hydroxide. So that H was removed from the water molecule, has been added to our conjugate acid, and this is the dissociation, the ionization that we should expect. And our Kb expression will set up the same way as our products, except instead of expecting hydronium up here, we should expect hydroxide. So this is an example of a Kb expression, and instead of the weak acid on the bottom for reactant, we'll have the concentration of our weak base. So again, here are some common weak bases that you may need these Kb values here for things like homework problems or other example problems in this worksheet. So let's take a look at sample exercise 15. Let me move this down here a little bit so we can see all the details of the question. Oh, actually, that is everything. So we're given here sample exercise 15. We're asked rather, what's the pH of a 0.15 molar solution of ammonia? So we have our table right above that will come in handy. So if we're asked to find pH, we have to recall that step one, we can find our hydroxide ion concentration from Kb values and our initial concentration, right? If we do an ice table, then we can find POH. We can take the negative log of that. And then in step three, we can do 14 minus POH. And then that will give us our pH. So that's one path to solving this problem. So let's write out our reaction and then the ice table below. So we're going to have that same dissociation here, right? We'll cancel out the water column. We get our equilibrium to establish. We get ammonium over here, and then hydroxide ions as our two products. So again, we can expect initially, just like with weak acids, that we have none of this. Our initial concentration here is 0.15 molar. Our change, everything is 1-to-1 coefficient-wise, so we have minus X on the reactant side, plus X on the product side. Let's see what we have at equilibrium. So we're going to add these terms together just like we did with the weak acids. So we have 0 plus X. So now let's set this equal to the Kb value. We know that our Kb expression looks just like above here with ammonium times hydroxide on top and then ammonia on the bottom. We're going to use the Kb value of 1.8 times 10 to the negative 5 to solve for X here. And again, since that is such a low value, we do not have to do the quadratic formula for this problem, as we've been able to avoid commonly in the past. So we have 1.8 times 10 to the negative 5th. This is going to be equal to x squared over 0.15 minus x. So we're going to assume that x is negligible. We'll get rid of that. We'll multiply both sides by 0.15. So then we get x squared is equal to that 0.15 times 1.8. Oh, we lost signal there for a second, times 1.8 times 10 to the negative 5. So we find the product over here. We can take the square root. When we solve for x, we'll find that x is equal to 0.00164 molar. Remember, this x is now our hydroxide ion concentration. So we can take the negative log of that, 0.00164 molar, plug that in. We get a pOH equal to 2.79. Now the last step here, to solve for pH, we're going to do 14 minus 2.79, and we're going to get our final pH of 11.21. This is basic pH, so that makes sense for ammonia.